Okay, so this poster is about building optimal decision trees. So decision trees, of course, are very famous ML method, and still variants of them, like the gradient boosted variants, are very used. They're usually built greedily, so we just make greedy decisions. We build them once, and it's been very successful, but you can also build them optimally. So you can look at all the possible decision trees you could build, and you could find the one which will, let's say, have the least misclassifications or something like that. Or you can say, you can build it optimally sparse, where you pay for every node, you have to save so many classifications. And this kind of trade-off, where you trade off like the size of the model versus the accuracy of the model, actually is effectively applying Occam's razor. And it turns out you can get very good test accuracy doing this, and you certainly won't overtrain. So the best approach out there to do this problem is dynamic programming problem, because it fits into that category. We were able to improve the dynamic programming solution by 3 orders of magnitude. And how do we do this? Well, we do better caching, because in dynamic programming you have to cache, find that you find the same problem again. You have to make sure you recognise that well. Better lower bounding, where we look at some problems we've already solved and use them to compute accurate lower bounds to problems that we haven't yet seen. And that allows us to wipe out looking at most of the problems, and a specialised approach for trees of depth 2, so we can sort of wipe out one of the n factors in the computation for trees of size 2. And that ends up making a big difference about how far you can go. So if you want to learn more, come to my poster.
Hi everyone, I'm going to talk about traffic assignment problem known as TAP, which is an important problem in strategic planning and traffic management. As an example, assume that we want to improve the performance of transportation system. We have a number of suggested projects. However, due to budget constraint, we want to select a subset of that gives the maximum benefits. To choose a good decisions, we need to assess how changes in infrastructure supply will affect the performance of transportation system and evaluate different options. This is when TAP comes into play and predicts how travelers choose their paths in a given network. So in this problem, TAP is at the lower level problem and needs to be solved many times. In TAP, we model travelers' behavior as selfish routers, selfish drivers, which means that they want to minimize their own travel time. So TAP algorithm, one main part of TAP algorithms is calculating shortest paths for lots of ODs. In this paper, we want to speed up TAP by reducing the shortest path calculation. Contrary to the traditional TAP algorithm, which employ shortest path tree from each origin to all destinations, we track edge changes and intelligently target important origin destinations. And here you can see the results that show our variation, which is in blue, outperforms other two state-of-the-art TAP algorithms. Thank you.
Hi everyone, I'm Edward Lamb. I've got a video here. So this project is about controlling robots in automated warehouses. So I've got a video of the robots roaming around a warehouse, and the goal is that they don't bump into each other, and they want to be able to pick up these triangular items in a warehouse and bring them to the other triangles pointing down. So this paper is about coordinating or controlling robots like this, or like other kinds of vehicles in an indoor environment, or like a container port. And this paper sits within a sequence of works on basically coordinating things going together or avoiding things going together. For example, if you have a specialized medical nurses and things like this going to elderly home care, you want them to come into the same place at the same time. Or if you have electric vehicles that go into a charging station, then you don't want them to come in to the charging station at the same time. These kinds of coordination problems, if you're interested in any of this, then come and speak to me later.
Well, hi, I'm Piyumi. I'm going to talk about our recent work on modeling certain important 3D shape properties of proteins. Well, proteins are the biomolecules of life as they perform important functionalities in our bodies. So these proteins are made out of linear chains of amino acids that fold into complex three-dimensional shapes spontaneously. And the shape of a protein can be expressed as a function of poses of individual amino acids in these proteins. For an example, you can see an image of a protein and then zooming out an amino acid and showing its pose. The question is, given a universe of experimentally determined proteins, can we model the distribution of these poses of amino acids in a statistical concise manner? So in our recent paper, we addressed this problem by deriving statistical mixture models that model the distribution of rotations along the bonds of these amino acids. And for that, we used MML framework. So MML is a Bayesian information theoretic framework that provides the optimal trade-off between model fit, in our case, explaining the underlying observed distributions, and then on the other hand, the complexity of the model. So in our case, that includes the number of components, the component parameters, and the weights of these components. And finally, we compared the performance of these mixture models with the state of the art, and we were able to show that our mixture models outperform the state of the art by 3 orders of magnitude in the complexity level, and they are able to provide around 20% compression when explaining the underlying distributions. And also, we have made available programs that utilizes these mixture models so that protein structure biologists can integrate them into their work pipelines so that they can be used in work like protein structure prediction, protein structure determination, and de novo protein design. So if you are interested in this work, please visit our poster. Thank you.
Yeah, I'm Li Zhen. So I think everyone here, most people here are using ChatGPT or some kind of chatbot. That's why I'm thinking about probably just it's better to introduce this paper here, which is recently accepted in the transaction of Association for Computational Linguistics, TACO for short. Actually, this is the work primarily done by Tao in his first year of PhD and supervised by Reza and myself. Okay, so if you use ChatGPT, maybe one of the problems you know is that it gets some hallucination problems, right? So it generates some responses, look like nature and look like quite confident, but actually, so maybe it's just irrelevant or actually not factual. Then many papers have started working on this for some time, but we look at this problem here as well, but we more focus on what are the underlying reasons for this, right? We believe that the key reason behind this is that the statistical model or the deep learning models, when they generate response, they rely on the correlations, which are spurious. That means that they rely on the correlation which they are not supposed to rely on. That's why they generate something actually less meaningful, right? So to tackle these problems, we make the first study in Dado research to study these spurious correlations, and then actually then we create data and also devise some kind of new solution to this based on causal discovery. Because the right way to use causal discovery, because actually it's about actually identify causal relations, right? Between random variable. Then we inspire these techniques, we apply them to identify actually come up with a solution which turned out to be the model agnostic, right? If you are interested to see that how our model achieve basically the performance actually similar to the human performance, even slightly better, then come to the poster. Thank you.